The intermediate value theorem allows us to make further conclusions about continuous functions. The way that this works is you first consider an interval on your function's domain. So you pick some value on the horizontal axis, plug it into your function, and find the output. And do the same thing for the right edge of an interval, find a number on the horizontal axis, plug it into your function, and find the output. Now that we have the two function outputs that correspond to the interval that we've picked for our domain, we can say that there's a number z, any number z, between those two function outputs. We'll be able to find a corresponding input value c, and that c will have to be between the values a and b. So remember, a and b is the interval for our input, so those are the range of values for x. We plug the a and the b into our function to find the function outputs, f at a and f at b. Then we can say, pick any z value that you want that lives between f of a and f of b, and I can guarantee you I'll be able to find a point on my function whose input had to be between a and b. So we can guarantee that for any z value between f of a and f of b, there will be a c that exists between a and b, so that if I plug c into my function, it will give me the output of z. This might not seem very interesting right now, but it does allow us to build upon other ideas later, so it's important to understand how this theorem works and what it allows us to conclude. Let's try using the intermediate value theorem to determine that a function has at least one zero. Recall that when a function has a zero, that just means that it passes through the x-axis. So at some x input, my function output should be equal to 0. We can see that that's true just by looking at the graph. We can see that this wiggly function will cross over the x-axis, but we want to use the intermediate value theorem to show this. So we need to pick two function inputs that will produce outputs of opposite signs. So let's start by picking something like 0 for our input. We'll evaluate f at 0. That's equal to -1. On our graph, we have just determined the left edge of our input, and we found the corresponding output. Now we need to pick another value to plug into our function, and we want this output to be on the opposite side of the x-axis. So we have a point that's below the x-axis. Now we want one that will be above the x-axis. I'll try pi over 2. Evaluating our function at pi over 2, I get positive pi over 2 because cosine at pi over 2 is 0. On our graph, we've just determined the right edge of our interval, and we found the function output is above the x-axis. And so we can see that the intermediate value theorem allows us to make a conclusion about any z value between these two outputs. A 0 is right at the x-axis, so we could consider z to be 0, and that does fit between the interval of our left edge at 0 and our right edge at pi over 2. Our function outputs are below and above this 0 that we're looking for. So the intermediate value theorem will guarantee that there is a point within this interval that corresponds to the output of 0. So we can guarantee that a c will exist between 0 and pi over 2. I don't know what that c value is, but I can guarantee that it'll be there. Now this theorem does have some limitations. So we just showed an example where you can conclude that a function has a 0. We picked points where the output of the function was opposite sign. So one point had a negative output, the other point had a positive output. But if I didn't know enough about this function, and maybe I picked 2 points and their outputs were both positive, I wouldn't be able to make a conclusion about the function having a 0. So on the screen we have two visuals. On the left, this is one where we can use the intermediate value theorem to determine the function has a 0. On the right, we cannot, and that's because the points that we've picked for our interval, they're both above the x-axis. So the 0 that we wanted to determine existed, it's not between the function outputs. In fact, it's below both of the function outputs. So in that case, we wouldn't be able to use the intermediate value theorem because our interval doesn't span across the x-axis. Another limitation of this intermediate value theorem is that we need to make sure that we pick an interval where the function is continuous. There are discontinuities out there, so think of the function 1 over x. If I wanted to show that there was a 0 using the intermediate value theorem, for example, I would not be able to use an interval that went across the vertical asymptote for that function. So we have to make sure that the function is continuous, so no jumps, no holes, no asymptotes, and we have to make sure that the points that we pick give us the vertical range for the value we're trying to guarantee exists. So if we want to guarantee that there's a 0, then our function outputs need to include the 0 on the y-axis. Otherwise, we won't be able to make that conclusion.